All right, so welcome back to part 3 of lecture 10. Now we're going to see the main applications, right? Which we're going to use Perron-Frobenius to prove the fundamental theorem of Markov chains. All right, so if you remember, we had that the return time from state I to itself was defined as like the minimum time t, such that if I start my Markov chain at state I, I'll go back to I at time t, right? And the expected return time is just like the expectation of this value, right? Okay, and now if you remember, we had this main theorem from last time, which is any finite, irreducible, and aperiodic Markov chain has the following properties. There exists a unique stationary distribution pi, where pi sub I is bigger than 0 for all I, right? Like a positive vector. The sequence of distributions will always converge to pi, no matter what the initial distribution is. And we can also compute explicitly pi I if we can compute this expected return time, right? That was the upshot. So today we're going to see the proof of 1 and 2, right? So, all right. So how do we prove this, right? So the way we prove this is quite simple, right? Look at the transition matrix of your Markov chain, right? If your transition matrix is non-negative, irreducible, and aperiodic, we know that we can apply Perron-Frobenius, and we prove items 1 and 2, right? Because we know that there will be a unique stationary distribution, right? And therefore, like this unique stationary distribution is exactly the vector of highest spectral norm, right? So, okay. So then, like, it just follows from Perron-Frobenius, right? And we know that every distribution will converge to pi because, well, what happens, right? Like, all the other eigenvalues are less than 1. So, in particular, what happens here is that if all the other eigenvalues are less than 1, all of them will tend to 0, and only the eigenvalue 1 will actually survive, which is the eigenvalue for pi, right? So this is the convergence that we saw last time.
How do we know that the eigenvalue is 1 for this?
Right, because you can compute that spectral radius, right? For Markov chains, the spectral radius is 1.
Oh, okay.
Right, you can always compute because your matrix is stochastic, right? So every, like, if you think about it, like every row of your matrix will sum to 1.
Yeah.
Right. So then you can just compute the spectral radius. So that, let's say that there's a practice problem. It will always be like less than or equal to 1. Okay. So, all right. Now, here's the thing. Let's just take a look at this when our underlying graph of the Markov chain is actually undirected. Okay. So an undirected graph corresponds to like time reversible kind of Markov chains, right? Because the same like oh, sorry, no, let me not say that. That's incorrect. So let's just say that our underlying graph is undirected. Okay. So if our underlying graph is undirected, which means that if I go from I to J, I can also go from J to I, right? The probabilities will be different, right? That's the difference here. Is the following. So if AG is the adjacency matrix of the graph G, and let's say that D is just a diagonal matrix with like the degrees of each vertex in the diagonal, right? So the vertex 1 has degree D1, vertex 2 has degree D2, and so on. What is our transition matrix for this Markov chain? The transition matrix is exactly this matrix, like IP times the inverse of the diagonal times the adjacency matrix. Okay? So now here's the thing, right? Note that in this case, if our underlying graph is undirected, it's very easy to guess what the stationary distribution is, right? Like you can just guess that pi sub I will be di over 2n. Okay, and if you just multiply this by p, you'll see that you get exactly pi. So this, for the undirected case, it's very easy to guess what the distribution is. So now we know that we have this like stationary distribution. But the question could be, well, like, okay, so how do we know that this is unique, right? Like, and that's kind of answering to Ryan's question in a sense, like, okay, how do we know that this is 1 or so on and so forth? So here we have one eigenvector with eigenvalue 1, right? And this is positive. Okay, so I'm just doing an example to showcase how you can always figure it out, right? So the undirected case is very easy. Now, what do? Our underlying graph is undirected. So we guess the stationary distribution. So, oh, there's this one. But the question is, well, is there another one? Right? There could be another one. Or this pi cannot be the largest eigenvalue, right? Like, as Ryan is saying, oh, there's a positive eigenvalue and there's a positive eigenvector. Okay, sure. But this eigenvalue 1 may not be the largest, right? Okay. So now here's the thing. Here's one way. This is only one way that you can see this, right? So if we have the adjacency matrix of the graph, we know the transition matrix. Now, this transition matrix is not symmetric, right? It's clearly not a symmetric matrix because this is a symmetric matrix, but then you're multiplying it by a diagonal, so you're breaking the symmetry. But you don't break the symmetry too much because P is similar to a symmetric matrix, right? If you conjugate P by the square root of the diagonal, you get that this is exactly a symmetric matrix, right? Like this is symmetric. And now, well, what do we know about symmetric matrices, right? We know by the spectral theorem that, okay, first of all, if P and P prime, like they're conjugates, they're similar, we know that they have the same eigenvalues, right? And we can map the eigenvectors of P prime to the eigenvectors of P, right? Just by doing the conjugation again, right? So we know that P and P prime, they have the same eigenvalues, right? And we also know that P prime has only real eigenvalues, right? And that's because of the spectral theorem. Now, moreover, we know that the eigenvectors of P are going to be like d to the minus half of Vi, where Vi are the eigenvectors of P prime, just because P prime and P are conjugates, right? And this diagonal is just positive numbers, right? I'm just multiplying each coordinate of Vi by a positive number, right? So, and moreover, we know by the spectral theorem that we can take VIs to form an orthonormal basis. What does it mean? That Vi and Vj, the two eigenvectors, are orthogonal, right? Now, here's the thing. We have that these guys are, each two eigenvectors are orthogonal, right? But we know that the graph, well, the graph is connected, is also strongly connected. So then we know that Perron-Frobenius applies here to this matrix P. And then what does Perron-Frobenius say? Perron-Frobenius said there's a unique eigenvector whose eigenvalue has maximum absolute value. And this eigenvector has all positive coordinates, right? And the eigenvalue is positive. But the thing is, remember, the VIs are orthonormal, which means that if there's one eigenvector with only positive entries, what happens to the other ones? There cannot be two of them with only positive entries. Does that make sense? So if there's only one, well, which eigenvector is this? It has to be pi, because the only eigenvector with only positive entries, right? So, and that's why, like, all the random walks will converge to pi, because we know that this is the one that has the spectral norm, right? So the spectral norm here is 1 in this case, right? So this is one way you can show for undirected graphs, okay? So, okay. So do you have any